Hey everyone! In this video we're going to be going over section 4.4, factoring trinomials. In particular, we're going to be factoring trinomials of the form x squared plus bx plus c. We're gonna be dealing with cases when this constant term is positive. We're gonna deal with cases when this constant term is negative. And at the end, we're going to deal with cases when instead of a leading coefficient of 1, we have a leading coefficient of -1. Up until this point in this chapter, we've been taking binomials like x plus 2 times x plus 3, and we've been multiplying them together. We've been using FOIL, or the distributive property, and we have been turning them into, well, let's do that. First, we'd get x times x for an x squared, and we'd do our outside. X times 3 would give us a plus 3x. We would do our inside. 2 times x gives us a plus 2x, and then we would do our last. 2 times 3 is 6. We'd gather some like terms, call that x squared plus 5x plus 6. So that's what we have been doing. What we want to do is we want to do this process in reverse order. We want to start off with trinomials like x squared plus 8x plus 15. And what we want to do is we want to come up with two factors, something like an x plus a p times an x plus a q, that when we multiply these things together, it'll equal x squared plus 8x plus 5. Well, let's use the distributive property on this right-hand side. Let's FOIL these two binomials together. Well, first, x times x gives us an x squared. Then we'd have a plus qx plus a px plus a pq. Okay, so I'm going to gather like terms over here, and I'm going to factor out the x. So over here can be rewritten as x squared plus, if I factor this x out, I could write this trinomial as p plus q x plus p q. And so now take a look at what we have. We want x squared plus 8x plus 15 to be equal to x squared plus p plus q x plus p q. And so we're going to, at this point, we use a method called comparing coefficients. That means the number of x squareds that we have on the right has to equal the number of x squareds we have on the left, which it does. We've got 1x squared over here and 1x squared over here. Moving down the line, the number of x's we have over here has to match the number of x's we have over here. That means we're looking for numbers p and q that when you add them together, they equal 8. And finally, going down the line one more step, we want numbers p times q when these two numbers get multiplied together, they equal 15. So at this point, I typically like to make a factor tree for the number 15. So the factors of 15 are 1 and 15. 2 isn't a factor. 3 is. 4 isn't. And then we get back to 5. And it'd be 5 and 3 and 15 and 1. Well, we don't need to deal with repeats. So now we want to check. Well, what about when we add 1 to 15? 1 plus 15 equals 16. So we don't want those numbers. But right here, 3 plus 5 is equal to 8. We have found two numbers. 3 times 5 is equal to 15, and 3 plus 5 is equal to 8. So that means we can let p be equal to 3 and q be equal to 5. I could have said p was 5 and q was 3. That part, how I assigned these values to these variables, that was done arbitrarily. We could have switched those, it doesn't matter. But now that we know what P and Q is, what we're trying to solve is this problem up here. Well, we know that x squared plus 8x plus 15 is equal to x plus 3 times x plus 5. And with factoring, you can always go back. You can always double check your work by working with this right-hand side. X times x, that's equal to x squared, plus 5x plus 3x, that'd give us an 8x, plus 3 times 5 is 15. It checks out. So this is what our process is going to be. We're going to take a look at the, well, for now, in 4.5, we're going to add a step. For right now, we're going to take a look at this constant term. And we're looking for the factors of the constant term. So let's write this down. Factors of constant term and I'm going to call that C, that add to leading coefficient of x term. And that would be denoted by the letter B. This C and that B, they're a reference to this thing I had written in the very beginning. X squared plus bx plus c. Tried to factor polynomials of this form. So we're looking for factors of the constant term that add to the leading coefficient of the x term. So let's do another example. Let's say in the directions for all of these problems are just going to say factor. So we want to factor. The thing we want to factor is x squared plus 9x plus 8. Okay, so this is all a problem will say. Everything from that line down. It'll just say factor that trinomial. Okay, so we look to our constant term. Well, first we're going to notice that, hey, that sign is positive. We have a positive constant term. I'll show you what to do with a negative constant term here in a couple examples. But for now, we've got a positive constant term. Cool. So we need to get these factors of the constant term. We need the factors of C. Well, so I make a factor tree for 8. Well, 8 is equal to 1 times 8. It's equal to 2 times 4. 3 doesn't go in, 6 doesn't go in. You don't necessarily, well, let's finish this example before I go there. So we have came up with the factors of 8. The factors of 8 are either 1 and 8 or 2 and 4. We would start to repeat and we'd get a 4 and a 2 and a 8 and a 1, and we don't need those. Not for the positive case. Then we go through and we add. 1 plus 8 equals 9. That's what we're after. 2 plus 4 is equal to 6, and that's not what we're after. We're after 9 because we're looking for factors of the constant term that add to the leading coefficient of the x term. This is our leading coefficient of the x term. So, 1 and 8. Those are our numbers. And we want to factor this polynomial into an x plus, well, on the back side we call that x plus p and x plus q. It doesn't matter which one, it doesn't matter which one you call which. So we can let p be equal to 1 and q be equal to 8. And we see that, and then just filling these in where they go. X plus 1 times x plus 8. You can always check factors. You should be able to go backwards. So x plus 1 times x plus 8, when we FOIL this thing out, x times x is equal to an x squared. X times 8 is equal to a positive 8x. 1 times x is equal to a positive x. And 1 times 8 is equal to a positive 8. Add everything together, and we'll get an x squared plus a 9x plus an 8. Right back to where we started. Just to label, you don't have to do anything beneath this line. All this down here is just a check. A check to make sure you did it correctly. Factoring is a reversible process. So if you ever multiply your factors out and you get something different, then you know you made a mistake somewhere. Check to make sure that you didn't make a mistake in your check, and then double check your factors real quick. Okay, so let's go on to another example. So once again, we want to factor. And the thing we want to factor is 20 minus 9y plus y squared. Okay, so it doesn't matter if we're factoring x's, it doesn't matter if we're factoring y's, we could factor z's, we could factor anything really. In class, I'd introduce you guys to more Greek letters. I'd have you factor alphas and gammas and stuff like that. But that's strictly just for getting you guys exposed to the Greek alphabet. So the point of that is there's no difference in the fact that this problem has y's and the previous two had x's. It's just a variable. The thing is, our technique is for trinomials of the form x squared plus bx plus c. So we need to rewrite this trinomial with the squared term first. So we'd get a y squared. Then we have some number attached to our variable. We've got some number attached to our variable, minus 9y. And we have this positive 20 floating around. Cool, so we did this just to rewrite. So, yeah, and we still have a positive, positive constant term. So we're looking for the factors of 20. Well, 20 is equal to 1 times 20. It's equal to 2 times 10, and it's equal to 4 times 5. After that, we're going to start to get repeats. But we want them to add to a negative 9. This is where it's different than the other problems. Because it's true that 1 times 20 is equal to a positive 20. But it's also true that negative 1 times a negative 20 is equal to a positive 20. Negative 2 is equal to, a negative 2 times a negative 10 is equal to a positive 20. And a negative 4 times a negative 5 is equal to a positive 20. I went through and I made all of these numbers negative. Your clue to do that is this symbol right here. That minus sign in front of that leading coefficient tells you to go through and make all of these negative. So we're looking for factors that when we add them together equal negative 9. Well, negative 1 plus a negative 20 is equal to a negative 21. A negative 2 plus a negative 10 is equal to a negative 12. And a negative 4 plus a negative 5 is equal to a negative 9. There we go. That's what we're after. We know that negative 4 times negative 5 is equal to a positive 20. And we know that negative 4 plus a negative 5 is equal to a negative 9. These are the conditions we were after. So it doesn't matter which we call P and which we call Q. I'll say P is equal to negative 4 and Q is equal to negative 5. We did this because we're trying to factor this into a... Now we've written x plus p and x plus q, which is fine. But p is equal to a negative 4, so this is going to be equal to an x plus a negative 4 is the same as minus 4 times x plus a negative 5, which is the same as minus 5. Oh, I have switched to x's. I'm sorry, you guys. Let's, we will say this is equal to a y plus p times a y plus q, which is equal to a y minus 4 times a y minus 5. Sorry, kind of habit to switch to x's. But like I just got done saying, it behaves the same whether you work in x's or in y's. We're just calling the variable a different name. So, let's see. So the next example, we're dealing with a negative constant term. So let's wrap this up. Let's put some things together. So for a positive constant term, here's page 1. For a positive constant term, for all of these, we're looking for the factors that add to 15 that add to this middle term. Not every problem, the factors that add to 15, but in this example. Okay. So we're looking for factors of 15, so we made a factor tree. 1 and 15, 3 and 5, 5 and 3, 15 and 1. And now we want both of our numbers in these columns to be positive because of this symbol. The positive or the plus sign in front of that 8. So we leave all these numbers positive. Then we go through and we add them because we're looking for numbers that multiply to 15 but add to 8. So these numbers multiply together to 15, and then we add them, and we want the one that adds to 8. Once you have two numbers, 3 and 5, it doesn't matter which you call P and which you call Q, because you can multiply in any order you want to. By switching these orders, you're really just switching these orders. Doesn't matter. Once you find your P and your Q, you're just plugging them into this form. So again, positive constant term. So we're looking for numbers that multiply to 8 that add to 9. We had 1 and 8, and we had 2 and 4. We wanted both of these numbers, or the numbers in both of these columns, to be positive because of that plus sign right there. That's why you have a positive 1 and a positive 8, a positive 2 and a positive 4. And we're looking for the factors that that add to 9. So 1 plus 8 is 9. 2 plus 4 is 6. Once we had the two numbers that multiplied together to equal 8, up here, and add together to equal 9, call one P and call one Q. Doesn't matter which one is which. Call one P and call one Q, and fill them out into this formula. They get tricky. We've got a positive constant term. The process is still the same. We want the factors of 20, 1 and 20, 2 and 10, 4 and 5. But this sign right here, this negative symbol in front of the 9, tells you to make all of these numbers negative. And the process is still the same. You add this column plus that column, and you're trying to find the numbers that when you add them together equal that negative 9. So yeah, I wanna leave it at that. We'll say more when we get there. So now let's factor some trinomials whose constant term is negative. Let's talk about something like x squared plus 17x minus 110. Now, the tricky thing here is that since this symbol is negative, we're still looking for two numbers that multiply together, P and Q, that equal, now it's supposed to be a negative 110. And we still want P plus Q to equal a positive 17. The tricky part here is that for two numbers to multiply together to equal a negative number, one of these numbers has to be negative and the other one can't be 0. So this is still where I start off. I always start off over here, coming up with the factor tree. Well, we've got, and I'm going to work, well, we'll say negative 110. So I know that 1 times 110, 1 times a negative 110 is equal to negative 110. I know that 2 times a negative, what would that be, a 55, is equal to 110. 3 doesn't go in there, 4 doesn't go in there, 5 does. 5 and what would that be, 22? Negative 22. Oh, and then 10 and negative 11. And now they're going to double back. We're going to have 11 and negative 10, 22 and negative 5, 55 and negative 2, and 110 and negative 1. Perfect. So on all the previous examples, I have, not necessarily all of them, I would stop once that repeat happened, once the columns on the, or the numbers in the left column started showing up on the right. When we're dealing with a negative constant term, I don't do that. I let it go all the way. Because if you look, every number appears positive once and negative once. Okay. So now go through and then treat each of these rows like a small math problem. 1 take away 110 is negative 109. Now 2 take away 55 is equal to a negative 53. 5 take away 2 is equal to a negative 17. Close, but we're looking for a positive 17. 10 take away 11 is equal to negative 1. 11 take away 10 is equal to a positive 1. 22 take away 5 is equal to a positive 17, and that's what we're after. Just to finish for good measure, 53 and 109. But we were looking for two numbers that when we multiply them together, their sum is 17 and their product is negative 110. Well, our goal is still the same, to turn this into an x plus a p times an x plus a q. And it doesn't matter which one we call which. We'll let p be equal to 22 and we'll let q be equal to a negative 5. Once we know the value of p and q, we can finish this problem off. Call it x plus 22 times x minus 5. Still the same process. We're looking for two numbers that multiply together to get this negative constant term. And then they still have to add to equal this number right here. The only thing that's different is when we have a minus sign, one of these numbers in each of these columns has to be positive, one of them has to be negative, and this is the process I came up with to make sure I get all my factors. It really eliminates most of the guesswork. This problem comes down to remembering the process and being able to factor that number. Okay, so the book gives you one real example of this, and it jumps on to some bigger and badder things. So let's follow suit. So we want to factor x cubed minus x squared minus 30x. And I told you that we're going to be factoring things of the form x squared plus bx plus c. What about this x cubed that popped out of nowhere? Well, if you notice, each of these terms has an x. So let's factor an x out of all of these terms. this thing is equal to x times x squared minus x minus 30. Now we have a polynomial of the form ax squared plus bx plus c. We want to come up with numbers that multiply to negative 30 that are going to add to a negative 1. Well, there's 1 and negative 30. There's 2 and negative 15. There's 3 and negative 10. And then there is a 5 and a negative 6. We can repeat. There'd be a 6 and a negative 5. There'd be a 10 and a negative 3. There'd be a 15 and a negative 2 and a 30 and a negative 1. And we go through and we do these small kind of problems in the rows. 1 take away 30 is negative 29. 2 take away 15 is negative 13. 3 take away 10 is negative 7. 5 take away 6 is negative 1. 6 take away 5 is 1. 10 take away 3 is 7. 15 take away 2 is 13. And 30 take away 2 is 29. Okay, all the factors of negative 30, and we added them together. We want the ones that equal negative 1. That means we want these numbers right here. It doesn't matter which one we call P and which one we call Q. I'll say P is equal to 6 and Q is equal to negative 5. But now look, I haven't saved myself enough space here, so I'll try and write it over here. We know that x cubed minus x squared minus 30x, well, that thing is equal to x times x squared minus x minus 30. But we know what that thing is equal to. That this leading x is along for the ride. Through this process, we figured out that x squared minus x minus 30 is the same as x I totally circled the wrong one. 5 take away 6 is not. 5 take away 6 is definitely negative 1, but I accidentally circled 6 take away 5. That's what I meant to circle. Sorry, my table got kind of messy. There we go. That's the one that we wanted. Yeah, I kind of fell off the line there, or out of line there. So, and that means I want to switch which one I call. I'll say that P is a 5, and Q is a negative 6. Sorry about that. I read my table poorly. That's where I was at. So we've got this trinomial, x squared minus x minus 30. We've figured out how that factors. That'll factor into an x minus 6 and an x plus 5. So when all of your exponents, okay, so let's say this. So notice how all of our terms have an x. Our first step was to factor that x out, and that x just hung along for the ride the entire time. This is our final step. So I feel compelled to ask you guys if you have any questions. Let's do one more example of those. Let's say we had an x cubed, and then let's say we had a minus 5x squared minus 14x. Perfect. So this is similar to the last one, a little bit different, but we want to factor this problem. So all of our terms, we've got an x cubed, an x squared, and an x. They all have an x, so your first step is to factor out an x from all of these terms. What's left over, we'd have an x squared minus 5x minus 14. Okay? Now, our focus is over here. This x is just along for the ride. Your job is to not forget to write it at every step. So now we want to factor this thing. Well, we're looking for the factors of negative 14 that add to negative 5. Well, the factors of negative 14 are 1 and negative 14, 2 and negative 7, 3, 4, 5, and we'll double back. Not 5. 7 and negative 2, and then 14 and negative 1. We want to go through and want to add these rows. 1 plus negative 14 is negative 13. 2 plus negative 7 is negative 5. So one we're after. 7 plus 2 is equal to 5. 14 plus 1 is equal to 13. I only continue just because I'm trying to show you guys every single step. You can stop once you get the ones you're after. Doesn't matter which one we call P, which one we call Q. I've been calling the number that comes first P, and the number that comes second Q. And so we did that because we wanted to factor this trinomial, or this trinomial into an x plus a p times an x plus a q, which for this problem, that's an x plus p, x plus q. And you can always go through and you can double check. X times x is x squared, minus 7x plus 2x gives us a minus 5x, and 2 times negative 7 is negative 14. If we were to multiply this x into each of these terms, we'd get back to our original. So when all of our terms have an x, factor out that x. You should reduce it down to this sort of trinomial, and then go through the same process. Don't forget to write the x at every step, and you should be golden. These do get a little bit more tricky. Let me find my notes real quick. Perfect, so I got a couple more examples for you. So let's continue on. We let's factor x to the 4th plus 2x squared minus 15. So this one's a little bit different. In that last problem that we did, the last two really, the last one that kind of went smoothly was this one, x cubed minus 5x squared minus 14x. If you notice, this is degree 3, this is degree 2, this is degree 1. So we factored out an x to get degree 2, degree 1, degree none. Over here, it's a little bit different. We've got a degree 4, a degree 2, and a degree 0. But this problem, we can't factor an x out of every term because there isn't an x in this constant term. You don't have to do this, but I'm gonna show you why I'm about to do the process. I'm going to come up with a new variable. I'm going to come up with this variable z. Let z, and z is going to be equal to an x squared. And if you take a look, x to the 4th plus 2x squared minus 15, well, that's the same as x squared squared plus 2x squared minus 15. So if we do this substitution, we can rewrite this as z squared plus 2z minus 15. And now we have something in the form that we've been working with. That's in the form x squared plus bx plus c. We've got a leading coefficient of 1. We've got a constant term, and we've got these x terms. So we're going to do this process that we have with this trinomial here. Okay, so we're looking for numbers that multiply together to equal negative 15 that add to positive 2. 1 and negative 15, 3 and negative 5, 5 and negative 3, and 15 and negative 1. We go through. 1 take away 15 is negative 14. 3 take away 5 is negative 2. 5 take away 3 is equal to a positive 2. These are the numbers that we're after. So, what this says is that z squared plus 2z minus 15, well, that's going to be equal to z plus 5 times a z minus 3. But the original problem doesn't have any z's in it. The original problem has x's in it. But what that means is x to the 4th plus 2x squared minus 15 has to be equal to z is equal to x squared. X squared plus 5, x squared minus 3. So you really can, you don't have to do this rename step and then write it in terms of z's and then convert back. What you need for this problem is this part right here, and the final answer. I say let z be equal to x squared just to make it look like what we have been working with. But the thing to notice is that it was degree 0, degree 2, degree 4. You would also solve problems like, we'll say, x to the 6th plus 2x cubed minus 15. This problem would be done in the same. All I did was change x to the 4th to x cubed and x squared to an x cubed. But this is still an x cubed squared plus 2x cubed minus 15. So, and then in this problem, I don't want to write z because I have z right there. We'd let y be equal to x cubed. And we'd go through and we'd do the same process. But it's when we've got degree 0, and then we have this degree, and this one is twice as much as that one. 4 is twice as much as 2, 6 is twice as much as 3. So that's the thing to be aware of. That's the thing you're looking for. We could say x to the 8 plus 2x to the 4th minus 15. The degree of the leading term is twice as much as degree of the middle term. And then I go through, I make a dummy variable, I substitute it in, I do work, and then I substitute it back out to get the final answer that we're after. If you are faced with a problem where the degree of the leading term is not 2, look for a trick. If you're getting thrown anything with degree 3 or higher, look for a trick. Look for a way to factor something out. Look if you can notice a pattern in the degrees and do a substitution to make it simple. If you're factoring something that has a degree 3, a degree 4, degree, anything greater than 2 in it, look for a little trick. Okay, so I've got 2 more examples for you. This piece of paper. Let's factor a negative x squared plus 5x plus 14. And notice how our leading coefficient is negative 1 instead of positive 1. The first thing we want to do is we want to factor out a minus 1 from each term. So that means a negative x squared plus 5x plus 14. That's the same as a negative 1 times a positive x squared, a negative 5x, and a negative 14. And now, this trinomial is in the form that we've been working with all along. In fact, this problem is going to now be very similar to this problem in that this thing out front, you just have to not forget to write it at every step. Now we want to factor this thing over here. We're looking for numbers that multiply to negative 14. Well, that's 1 and negative 14. That's 2 and negative 7. This one's going to work for us. 3, 4, 5, 7, and negative 2, and 14 and negative 1. 2 take away 7 is negative 5. Or, I wrote 15. Negative 5. Okay, so doesn't matter which one we call P or Q. We wanted to factor this thing into a negative 1 times an x plus a P times an x plus a Q. I'll let P be equal to 2 and Q be equal to negative 7. So this is equal to a negative 1 times an x plus a P times an x plus a Q, which is a negative 7, for our final answer. Oh, I forgot to write the answer down. That's fine. We can always double check this answer. X times x gives us an x squared. X times negative 7 is a negative 7x. Plus 2x gives us that negative 5x. And 2 times negative 7 is negative 14. Fine. I do want to warn you. I remember probably why I didn't write it down. There's something odd with the answer. I'm fine with your answer like this. I believe the book takes that minus 1 and it factors it back into one of these terms. So I believe the answer in the book is either put the minus 1 in with this first factor, would be a negative x minus 2 times an x minus 7, or if we put that minus 1 in the second term, x plus 2 times a negative x plus 7. I can't remember which one the book has. This is where I would encourage you to stop as compared to putting that minus sign back in, because after all, in this previous example, we never grouped that x back in. So once we pulled this minus sign out, it feels a little unnatural to me to push it back in. That's different than this process we've been doing all along. So I leave it floating around out front. There's also there's a theorem in mathematics that says that you can pretty much write any polynomial as we'll call it a times x plus c1, x plus c2, x plus c3, and these go on until you have x plus c n of them, until you've got n of them. So if every polynomial can be written as the product of these factors and some leading coefficient, it makes sense to leave this polynomial as the product of some factors and a leading coefficient as compared to trying to push it back in. It's kind of a long-winded tangent telling you to leave your answer in this form, though these are definitely correct. There's reasons for writing it like this. So the final problem, the biggest and baddest of them all in my opinion, is when we have multiple variables floating around. We've got an x squared minus 2xy and a minus 48y. So this problem is going to work the exact same as the previous problem. We're still looking for factors that multiply to negative 48 and add to negative 2. So let's go through and do that. So we want the factors of negative 48. Well, that's going to be a 1 and a negative 48. That's going to be a 2 and a negative 24. A 3 and a negative 16 it would be. 4 and a negative 12. 5. 6 will go in there. 6 and a negative 8. Then we would double back. 8 and a negative 6. 12 and a negative 4. 16 and a negative 3. 24 and a negative 2, and 48 and a negative 1. Okay, and then we're looking for the numbers that add to -2. Well, 6 plus a -8 is equal to a -2. And this is what we're going to be after. The thing that changes, well, we can let one of these be P and one of them be Q. The thing that changes is that our factors are changing. We want an x plus a py times an x plus a qy. How do I know that the p and the q are attached to the y and not attached to the x? Well, if you go to FOIL this thing out, the first thing we're going to do is we're going to multiply x times x. And we've got a leading coefficient of 1 over here, so we'd better have a leading coefficient of 1 over here when we multiply our x's together. These y's, they've got a number floating around. They've got that -48 floating around. So we know that the y's are going to have some number attached to them. So we've gone through, we've done the same steps as before. X plus a p plus py times x plus a q, -8y. So it's not really better, it's just different. It looks a little bit different because we have these two variables floating around. We've got x's and we've got y's floating around. Well, that just tells you that your answer needs to have x's and needs to have y's floating around. We're still doing an x plus p and an x plus q, except for in this time, since we've got those y's, it's x plus py and x plus qy. Still looking for factors of the last number that add to the second number. We were able to do that. Factoring, so that's it for this lesson. Go off and do 1 through 41, every other odd. I gave you every other odd so you can easily do more odd ones if you want. For better or for worse, I'll give a shameless plug to wolframalpha.com. I think my print looks worse than my cursive. Check out wolframalpha.com. If you plug in a polynomial like x squared minus 2xy minus 48y squared, if you plug that thing into Wolfram Alpha, hit enter, it'll kick you out. I wrote p there. X plus 6 times x minus 8, 6y, x minus 8y. Sorry about that. P's and 6's, they apparently feel similar when I write them. So if you plug trinomials like this into wolframalpha.com, they'll kick you out the factors for it. I tell you that because factoring is something that just takes time. It's a technique that doesn't really go away, and it definitely, I try and turn it into a process by having you guys construct this factor tree. But yeah, it takes time to get good at factoring. So if you need more help, this website will kick you out the answers at least. That'll tell you if you did it right or not. It won't tell you the steps for it though. And you can always check your work. Like I said, once you have factored something, you can always go in reverse to see if you get back to the original. But it's also good to get kind of that instant gratification of knowing if you did a problem right or not. Go off, like I said, do 1 through 41, every other odd. That's going to be due this Wednesday. That's 4/22 is when it's due. We'll have a quiz due that day as well. Yeah, factoring trinomials. Next time I post a video, our leading coefficient isn't going to be 1. This is one of the techniques that keeps on coming back over and over and over again. It definitely helps to get good at factoring. Just because I know we go over it in 151. When I teach calculus, by the time I teach calculus, factoring, students will have a lot more experience with factoring. They'll be able to do it quicker. This is really just pattern recognition, and after you do enough of them, you guys will start to recognize the pattern. But factoring in calculus, factoring doesn't really go away. That's where you kind of got a big chunk of homework here. It's worth it to go slow and try and figure these out. If you guys get stuck, shoot me an email. I'm happy to help you. Good luck with your homework, everybody. Bye-bye.